Late one evening, you look up at the night sky and wonder what might be waiting beyond the stars you can see. For centuries, humans have used telescopes, star maps, and rocket ships to probe the cosmos. Now, artificial intelligence is expanding that exploration in ways we never imagined. This is AI in space exploration, the final frontier of machine learning. A deep dive into how algorithms are becoming vital collaborators, working alongside astronomers, engineers, and even robots on distant planets. If you're as curious about the universe as I am, please consider subscribing. Your support helps us travel to the cutting edge of technology and share these awe-inspiring possibilities. When we think about space exploration, images of towering rockets or historic shuttle launches often come to mind. Yet behind the scenes, AI is doing some of the heaviest lifting. One major application is data analysis. Telescopes like the Hubble or the newer James Webb gather staggering amounts of information. Terabytes of images and spectra from galaxies millions, even billions of light years away. Sorting through all that data manually is almost impossible for humans, so scientists train machine learning models to spot anomalies. Exoplanets that dim a star's light in telltale patterns, or subtle cosmic structures that might indicate the presence of dark matter. In mere hours, an AI can sift through what might take researchers decades, flagging interesting leads that astronomers can follow up on. It's a time saver of cosmic proportions, allowing us to comb the universe more thoroughly than any single person or team ever could. Then there's the matter of mission planning. Deep space missions require enormous precision. Think of a rover heading to Mars, or a probe swinging by Jupiter's moons. Orbital mechanics are unforgiving. Get one calculation wrong and your spacecraft might end up sailing into oblivion. Traditionally, engineers painstakingly worked out trajectories, factoring in gravitational assists, fuel constraints, and communication windows. Now, AI is stepping in to help optimize these routes. By analyzing countless simulations, machine learning systems can recommend flight paths that minimize energy usage, shorten travel times, or ensure the craft arrives at just the right angle to enter orbit. NASA's Jet Propulsion Laboratory, for instance, uses AI to search for novel mission designs that a human might not conceive. Imagine an algorithm discovering a gravity assist trick that we've never tried, saving years of travel time or slashing the required fuel by half. That's the power of letting a machine explore the near-infinite possibilities of spaceflight. Of course, the most visible AI contributions often happen when we land on other worlds. Mars rovers like Perseverance or Curiosity are partially autonomous, thanks to advanced software that helps them navigate rocky terrain, avoid obstacles, and conduct scientific experiments without waiting for humans to micromanage every move. Light signals from Earth to Mars can take anywhere from 3 to 22 minutes to arrive, depending on orbital positions, and then the rover's response takes just as long to get back. If these machines had to rely on real-time human guidance for each and every turn, they'd hardly budge. Instead, AI modules allow them to chart safe paths, adapt to unexpected sand dunes, and decide which rock formations might be worth a closer look. Over the course of a single Martian day, a rover can roam a surprising distance, all while beaming back crucial updates on what it finds. This autonomy isn't just limited to rovers. Consider satellites orbiting Earth or other planets. Some use AI to identify cloud patterns, measure atmospheric changes, or track storms. They can autonomously retarget their instruments if they detect something unusual. Maybe an unexpected volcanic eruption on Venus, hypothetically, or evidence of new meteor impacts on the lunar surface. Instead of awaiting instructions from mission control, these satellites act on their own, maximizing the science they deliver back home. It's like having a team of robotic scientists in orbit, each making on-the-spot decisions about what data is most critical. We're also seeing AI pop up in the hunt for exoplanets. Observatories such as Kepler or TESS gather brightness curves from hundreds of thousands of stars, looking for the faint dips in light that occur when a planet crosses a star's face. Not every dip is a planet. Some are artifacts, binary star systems, or instrumental noise. Machine learning excels at telling these categories apart, boosting the odds that a newly flagged candidate is indeed a planet. Over the years, AI-based approaches have led to the discovery of numerous worlds. including some that lie in the habitable zones of their stars. By speeding up this process, we inch closer to that tantalizing possibility of finding an Earth-like planet with conditions for life. Another fascinating frontier is the potential for AI to guide off-world manufacturing or resource utilization. As space agencies plan missions to the Moon and Mars with an eye toward long-term habitats, we'll need to figure out how to use local materials, like lunar regolith or Martian soil, to build structures or produce vital resources. Real-time AI systems could oversee automated mining robots, analyzing the composition of soil or rock and deciding where to extract key elements. They might also adapt on the fly to changing conditions, like a sudden dust storm or a hardware failure. This is critical in environments where human intervention is limited or hazardous. A single glitch could shut down the entire operation, but a robust AI could reroute tasks, deploy backup equipment, or shuffle priorities to keep the mission on track. Of course, all this capability comes with a set of challenges. One major hurdle is bandwidth and latency. The deeper you go into space, the longer it takes for signals to travel. That's exactly why AI has to be capable of localized decision-making, because waiting for Earth-based mission control can be impractical. But building hardware robust enough to handle advanced machine learning in such extreme environments, radiation, temperature fluctuations, dust, is no small feat. Rovers and satellites often have limited processing power and memory. Engineers must craft specialized AI algorithms that thrive in edge computing scenarios, which is a fancy way of saying the system processes data on the spot rather than relying on a supercomputer back on Earth. Then there's the question of trust. If an AI system decides to override human commands because it deems a certain path or action safer, do we just let it? Missions worth billions of dollars ride on these decisions. As AI becomes more autonomous, tension can arise between granting it freedom and maintaining human oversight. The same conversation is playing out in other industries, like autonomous cars or military drones. But in space, the stakes feel heightened. One glitch in orbit could mean losing not just data, but an entire mission that took decades of planning. The push for explainable AI is partly motivated by such concerns. We want to know why a machine made a particular choice, so we can trust or correct it accordingly. Another moral dimension is the possibility of unintended consequences. Imagine an AI scanning the surface of a moon, deciding which samples to collect. If it overlooks something profoundly important, like a sign of microbial life, because it didn't match any known pattern, we might miss a scientific breakthrough. Alternatively, if it starts drilling in a spot that it incorrectly deems safe, it could damage precious geological features. As AI systems get more embedded in mission planning and execution, these scenarios become real enough to worry about. That's why space agencies are emphasizing a synergy between AI and human experts. The idea is to let AI handle the drudge work, data parsing, hazard avoidance, repetitive tasks, and keep humans in the loop for big-picture judgments. But let's not lose sight of the staggering benefits. If you've followed announcements about the James Webb Space Telescope, you've probably heard about the massive data streams it sends back, images capturing cosmic structures billions of years old. AI can scan these images for patterns hinting at early galaxy formation or signs of phenomena we've never theorized. Similar approaches can help identify gravitational waves or interpret signals from pulsars. In effect, machine learning can open new windows on the universe, revealing hidden structures or relationships that even the best-trained human eyes might never spot. It's almost as though we're deploying extra brains, tireless, hyper-focused digital brains, to do the cosmic detective work on our behalf. One aspirational vision is the creation of a planetary intelligence network, an integrated web of satellites, rovers, space telescopes, and Earth-based research stations, all exchanging data in real time. AI nodes would filter out noise, highlight emergent patterns, and direct resources where they're most needed. For instance, if a far-off probe detects an unusual burst from a distant star, it could instantly signal a nearby space telescope to pivot and capture more data. All this would happen in seconds or minutes, without waiting for a chain of human approvals. It's a synergy that could accelerate discovery, pushing the boundaries of what we know about everything from exoplanet atmospheres to cosmic inflation theories. We can't forget the intangible excitement factor. Space has always captured our collective imagination, from the Apollo landings to the Mars rover selfies. Now with AI in the mix, we're on the verge of an era where robotic explorers aren't just remote-controlled gadgets, but semi-autonomous partners. They might build habitats on the moon before the first astronauts arrive, or map out the best route to a Martian ice deposit for future colonies. They could study cosmic radiation up close, adapting their mission parameters as they learn. It almost feels like science fiction turned real, a saga in which humankind and machines collaborate to expand our cosmic footprint. Still, it's wise to keep a balanced view. AI isn't a cure-all. Missions can still fail due to hardware issues, underestimating radiation, or plain old bad luck with an asteroid collision. AI also has blind spots. If it's never been trained on a certain type of terrain or cosmic event, it might be just as clueless as we are. The complexities of spaceflight require a continuing partnership between talented human teams and these advanced algorithms. But that partnership can be powerful, allowing us to go further, stay longer, and learn more than we ever thought possible. If delving into the final frontier with the help of AI intrigues you, I encourage you to keep tabs on the major space agencies, private companies, and research labs pioneering these breakthroughs. Whether it's NASA's Perseverance rover handling its own hazard avoidance, ESA's advanced satellites reorganizing themselves for maximum Earth observation, or SpaceX's Starlink network adjusting satellite orbits via machine learning, the future is unfolding in front of us. And if you want more content exploring these frontiers, subscribing to this channel is a great way to stay in the loop, so you can see how each new development propels us deeper into an era where human ambition meets algorithmic ingenuity. Thanks for joining me on this epic journey through AI's role in space exploration. Together, we've glimpsed how algorithms transform raw data into cosmic insights, chart complex trajectories in an ever-shifting solar system, and help robotic explorers act independently on distant planets. It's a story of synergy, human curiosity amplified by machine intelligence. And as AI continues to evolve, who's to say what new cosmic secrets we might unlock next, or how far these robotic partners might carry us into realms we once considered unreachable? One thing's certain: as we look to the skies, AI will be right there with us, forging a new chapter in our quest to understand the universe.